Frank Schirrmeister is Executive Director of Strategic Programs, System Solutions in Synopsys Product and Market Group, and drives the strategy and narrative for the front-end solutions for silicon to systems design, from early system software through to hardware-assisted verification and verification IP.
So, sorry for the technical snafu. I'm calling in from the US, so it's rather early, but it's okay. I'm happy to be with all of you in the UK today in the morning, talking about hardware-assisted verification, chiplets, and AI. If you don't see anything, if you don't see the slides, please let me know, but I think we will be fine here. The obligatory notice, this is not confidential, but there any forward-looking statements and so forth are, of course, subject to these notices here. I'll talk briefly about the industry trends and challenges, pervasive intelligence, hardware, software, interfaces, architecture, talk also very briefly about the chiplet verification challenges, some of the scaling laws we are with, power consumption, verification phases, and then talk about the role of prototyping and emulation, specifically in the context of emulation, the modular, in the context of verification, the modularity of verification, which we are facing in this new era, if you will, and then the role of software. And I will have some examples from users sprinkled in. A lot of you may have seen a version of this slide again before from some of my colleagues at Synopsys. We have this era, we call this the era of pervasive intelligence, where a digital transformation of industries is underway from data center through networking, all the other industries, automotive, enterprise software, PCs, gaming, with semiconductors appearing everywhere and semiconductors driving a lot of the digital transformation. And then when you look into AI in this context, that's driving a lot of the chiplet challenges. Who's better to ask than Jensen at NVIDIA himself? This is from his CES keynote, where he was talking about the new scaling laws, how we do pre-training scaling. That's the classic LLM post-training scaling, where you have optimization of large language models, and then test time scaling, where it's really getting into the reasoning portion of AI, and you have very different requirements in each of those phases, in each of those compute requirements, from model size, data set size originally, through performance, efficiency, domain specificity and adaptation in the post-training phase, and then latency, throughput, cost, memory footprint, and of course, we're all worried a bit about the energy consumption. That's how you get from this formal learning through the mentoring, coaching, and the long thinking. This is really for building AI chips. I'm here at the Design Automation Conference in San Francisco today, and for the last 2 days, AI and the implementation of it and using it for verification has been center stage for the last couple of days here. And conversely, for the actual chips that NVIDIA has been talking about, you get this new scaling, new matrix in here, where it's really about performance per watt that Blackwell improved, and the amount of data that is used, with twice the internet data being used every year, added for the next couple of years. So that translates for us in the chip world into complexities that really compound here. And we consider at Synopsys here hardware being the keystone for ensuring functionality, power, and performance, hardware-assisted verification, that is. And it's really addressing these compounding complexities of software, which has been growing very significantly, as shown on the right, and it's predicting to grow further. Hardware, we have everything from the very complex Blackwell to smaller chips. We have really 2 orders of magnitude of design sizes to deal with. You have a variety of interfaces growing at different throughput levels year over year, with AI, with the switch transformer, driving it with much more growth than the some of the interfaces are growing. So as a result, you need to be very architectural, clever to implement these architectures for AI in chiplet-based designs. Typically, that's where you have the optimization of the chiplet interfaces here. And then from a verification perspective, given that we are all here in this audience are worried about verification, it's really quadrillions of cycles that need to be run to do the verification. I put some sources here in the bottom. You can read up some of those data on where this is coming from. And there are really three elements which drive where AI drives this extreme performance. One being the compute itself, with over 4%, 4 times growth per year for the training compute needed for models. You have memory complexity that's growing also in a factor of 2 over 3 years if you look at the evolution of HBM over time. And the third bit is the interconnect, how you connect these chips into systems using Ethernet, using PCI Express. Again, driving here with PCI with about twice the performance and throughput every 3 years. And you have the evolution of Ethernet speeds here on the right. All of that compounded together in one graph, as you see here in this chart, with a couple of more growth laws added as with Moore's law, DRAM bandwidth, gets this requirement of a very wide range of optimizations dealing with the system complexity, mix of different types of computing, CPUs, GPUs, AI, FPGA, accelerators, different fabrics. So you have a really, really difficult architectural challenge, which you then need to verify. And to give kind of a state-of-the-art system verification challenge that we are facing today, this, of course, is not actually a real chip, but who was at the keynote or saw it of NVIDIA, this Grace Blackwell NVLink 72, which is this box here, this rack on the left. If you would put all of that onto one wafer, so to speak, with all, and if you would put it into chiplets, it would get you to these 130 million trillion transistors, which is, of course, quite out there, with really 1.4 exaflops, with what recent boom supercomputers would be, and the memory bandwidth of the internet every second with these 1.2 petabytes per second. So that's kind of the challenge of what we are verifying. And luckily, verification happens, of course, in phases. We start with simulation at the IP, at the processor level. We start with the subsystem verification that's often done in simulation. Then you get to what we used to call a system on chip, now becoming a chiplet, which goes into a multi-die setup where you have various chiplets of various types, computing, connectivity, memory, integrated in a multi-die setup. And hardware-assisted verification is really the keystone that links what used to be done in simulation with the quadrillion of cycles you need to do in silicon. And that's why hardware-assisted verification is so critical for the verification process here. So very early on, before you even put on the first line of RTL, you may want to look at the impact of your multi-die architecture on your system KPIs, where you have different ways of partitioning. You can taking the functional requirements into physical constraints, looking into different ways to put your chiplets down, mapping of workloads into data structures, looking at the traffic across chiplet boundaries, the memory architectures you need for that, and really looking at performance and power analysis early on, analyzing the resulting impact of the different chiplet architectures of your on your system. And you, of course, go round and round in the pre-RTL architecture phase. That's where capabilities in our offerings around the platform architect product family fit in, connecting to the chiplet implementation flows we have within Synopsys here. If you look into the requirements for verification, this gives you a couple of decades of examples, in this case, starting with the Intel processors. Myself, my first chip was somewhere here where I put the vertical axis with the amount of cycles needed in the early 90s, where we had actually, we would basically manual generate test cases. This is a manual ad hoc hardware-directed test you see in the bottom. We then invented things like ERM, VMM, OVM, System Verilog. This is a whole constrained random phase somewhere in the 2000s. We added in the mids, we added Accelera, the portable stimulus, and we got more and more test and verification requirements. We are now again in the phase these days where when you look at challenges like the latest chiplets, that the requirements for generating these tests kind of outgrow what humans can do. So it will be what humans can do manually, so and with existing techniques. So we are looking these days into really fitting and closing this test generation productivity gap. Hardware assisted verification, of course, plays a big role. If I'm obviously, given that I'm with Synopsys, I put here the prototyping and the emulation solutions from our side as well. But this is a broad industry trend that the chip capacity is really outpacing the capacity of the emulation in what we would refer to as single model setup. So you are naturally starting to modularize your verification by plugging the different chiplets into different parts of the into different prototyping systems, emulation systems, and connecting them on the outside. And I will jump in